This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is gas in cylinder with piston. Here's the geometry. We have a cylinder, and inside is a piston. It starts off at one position, and it moves to a new position. And the piston is trapping a gas. We're told that the process is pressure times volume is constant. We're told that initially we know the pressure and the volume. And we're asked to find the work if the volume changes to this value, 0.3, which is 3 times the initial value. And in part B, we're asked to find the final pressure. The way we're going to do this is we're going to, part A, find the work. We're going to use the definition of work as the integral from 1 to 2 of P dV. This will give us the area under the process curve. So here's a PV picture. We can work this integral if we can use the process information to find pressure. I'll say need pressure as a function of volume. And we can do that. It's just going to be P is equal to a constant divided by V, just solving that relationship. Let's plug that into the integral. So work is going to be the integral from 1 to 2 of C divided by V dV. We can work that guy. Let me scroll up a little bit. We can work that. That's going to be a constant will come out of the integral. dV over V integrates to log. And we're going to evaluate the log of V from state 1 to state 2. Let's keep going. I'm going to write this as constant times open bracket. Natural log of V evaluated at state 2 is V2 minus the other condition. It's going to be the natural log of V1. Okay, we can work this if we can get a value for C. Once again, from the process curve, we're going to use P times V as a constant. Well, let's evaluate it at state 1. I know both P1 and V1, so that's what I'm going to use here. So combining these two ideas, I'm going to have the work is P1 V1 times this relationship. Then I'm going to combine them with a trick using natural logs. Natural logs were invented so that division could be replaced by subtraction. So the log of V2 minus the log of V1 is the same as the log of the ratio of V2 over V1. Let's put some numbers in. The work is going to be, let me scroll back here, where's P1? P1 is 2 bar. I'm going to write that as 2 times 10 to the 5th newtons per meter squared. V1 is 0.1 meters cubed. And then I've got the natural log of the ratio of V2, which is 0.3, divided by V1, which is 0.1. The units cancel out there. When I can crunch this and get a number, the number is going to be 21,970. And the units are newtons per meter squared times meters cubed, which is Newton times meters. That's the same as a joule. Okay, now I'm going to choose to keep 4 digits because the implied precision is pretty low. Precision is 1 digit. I certainly don't need a lot of digits for the answer. 4 is the most an engineer could need. All right, that takes care of part A. Part B says, what's the final pressure? Well, once again, we can use the process relation. If PV is a constant, then P1 times V1 is also equal to P2 times V2. We can solve for P2. That's going to be P2 is P1 times V1 divided by V2. Putting some numbers in. P1 I'm going to write as a 2 bar. V1 is 0.1 meters cubed. V2 is 0.3 meters cubed. And when I crunch that, I get 0.6666. I could keep going. I'm going to stop there. I guess we could put a line over it because it does continue. Again, I'm going to choose 4 digits. A couple comments about this solution. One is that as the volume goes up, the pressure goes down. Again, that's from the process relation, from P times V equals a constant. Can we create this process? Is there an actual process associated with PV equals constant? Yes. If we take a gas and we expand it at temperature equals constant. And how could we do that? We could do that with a slow expansion. A slow expansion with heat transfer. All right, let's take a moment to recap. We've got a cylinder with a piston trapping gas, and it goes from state 1, expands to state 2, and the process relation is P times V equals constant. We use that process relation to find pressure as a function of volume and work an integral. And when we crunch some numbers, we decided to keep only 4 digits because the implied precision of the given data was low. Engineers generally don't need a whole lot of digits. In the second part, once again, we used the process relation to find the final pressure, and we decided to keep 4 digits. If you remember that engineers have precision limitations, then all will be well.